Hello, hello. We're here in Copenhagen and I've got Ben Kennedy with me. Ben is from the University of Canterbury in New Zealand, and he is really interested in the Krafla Drilling Project, and he's involved in that, and I'm fascinated by the idea of drilling into volcanoes. So Ben, would you be okay with answering a few questions about this?
I'd love to, yeah.
Yeah, great. So tell me, what's the big plan about drilling into this volcano? Why is it important?
So to me, it's the final frontier, right? You know.
It kind of is.
Yeah. I mean, we've been to space, right? We've been to the moon. We've been down to the bottom of the oceans. We've never been into a magma chamber, right? Mm-hmm. So I don't know. It's a completely fascinating frontier science.
I think Jules Verne was the only person who ever been down there, but you know.
Yeah. Yeah. So we want to learn what are magma chambers really like. I mean, as petrologists and volcanologists and geophysicists, we argue, well, we argue quite a bit.
Absolutely, yeah.
What are they like? Are they big blobs of liquid? Are they accumulations of crystals? We just have no idea. How deep are they?
That's right.
Are they 20 kilometers? Are they 2 kilometers? And the incredible thing about Krafla is they have been into a magma chamber, so by accident. So.
Yes, that was a few years back. I read about this and helped me out. My recollection is that accidentally the drill bit was ending up in a bit of rhyolite kind of magma, and surprisingly no big explosions, and the rhyolite was kind of, well, it came out as glass, and it was rather crystal poor. It had low delta oxygen, low delta 18O oxygen, typical for Iceland. So a lot of intriguing things that we learned from this. But why is it that people want to do it again?
Well, they weren't prepared for it. So this, you know, the original was a geothermal drilling project. They were specifically trying to not hit magma, right? So they were trying to get to you know, supercritical steam. Mm-hmm. They wanted to generate more power. And so now we want to go back there and this time be prepared. And I mean, one of the wonderful things is this drill hole was extremely productive for geothermal energy for a number of months after they drilled it. So it's actually an incredible resource. I mean,
yes.
Normally if you drill into continental crust, you know, you might get 50, 100 degrees. If you drill into an active geothermal system, you might get 200, 300 degrees. Mm-hmm. You drill straight into a magma chamber, you got 900 degrees, right? That's a lot hotter. You can generate a lot more energy that way. So from an energy point of view, it's very exciting. For monitoring your volcano, it's extremely exciting, right? You could use the analogy of, I don't know if you're a doctor and you were, you know, okay, Val has a temperature that is
probably too hot, but
of, you know, whatever it is, but then if you really want to find out what's wrong with Val, you need to have a look inside and see, you know, see what's going on.
Oh dear, yeah. No, I get your drift. Do you think that there's any major dangers if you accidentally drill into magma, or as they have done a few years back? There could also be accidentally, you know, extremely overpressured gas pockets or things like that. So do you feel there's a risk associated with that?
I mean, I think there's always a risk with drilling. Mm-hmm. Drilling into the earth is inherently dangerous. Drilling into geothermal systems is inherently dangerous. They've had blowouts and things like this previously at geothermal areas. You know, I think in this example is the fact that they've drilled it once for sure, maybe a previous time as well. Also in Hawaii and in Kenya, the same thing happened. A geothermal company accidentally hit magma, and again in those two places it didn't blow up. We didn't cause a volcanic eruption. So now it's happened 3 different places, and none of those times has it caused an eruption. So you know, it's one of those things that, you know, it's the beginning of a bad sci-fi movie, right? But I think we can be confident on those, at least at those locations where it's happened before, it hasn't caused eruption. That's not to say it can't. Maybe if you drilled into Krakatoa or something like this, you know,
it might be more serious.
different story.
We'll come to this in a minute, because NASA released this kind of future vision that you might be able to cool down volcanoes, super volcanoes that are building up with these, you know, man-made drill holes. I wouldn't want to be the driller, but in theory, yeah, maybe there's something to it. But you have some rocks for us, don't you?
Yes.
And maybe you want to show those first before we go into the wild part of it.
So, anyone can see this. This is a piece of obsidian. So,
right.
Dragon glass. And this is exactly the type of rock that turned up when they drilled into the magma chamber in Krafla.
Yeah.
So they felt the drill bit suddenly started going back up the drill string.
Oh, that's what happened.
And they knew that something was going on. Things started melting that shouldn't be melting. And then the drilling mud that's come up is suddenly chocked full of glass.
Right.
Because your magma, your liquid magma, is suddenly quenched because you pump lots of cold drilling mud down as you're drilling, and cold water down, and that quenches the magma, turns it instantly to glass, and that glass is returned up in the drilling mud. So we have lots of little bits of glass like this, and we're doing research now at the University of Canterbury on these little tiny chips, and we're measuring exactly how much water and gas is dissolved in them, to inform, okay, what was the magma like, what was the viscosity, how sticky was the magma when it was coming up.
The drill bit that went upwards, I guess that's from the overpressure in the system, but it didn't have enough overpressure to blow the whole drill bit out. It just lifted it up. Is that right?
So it came up, and then it was too viscous. It was too sticky, so it solidified before it particulated. There are some bits. So here we actually have some pumice. So some of the material that was returned in the drilling mud was pumice. So there's some bubbly stuff.
Some was frothed up, yeah.
Yeah, and then there's some, you know, the dense black stuff. So you get both.
And do you think the frothing happened because of the decompression once the hole was made, or do you think it was maybe from the shear of the drill, or?
This is one of the questions that we're looking into. Is the bubbles that you see, were they there before the drilling started? Or were they induced by the drilling? And this is a question that we're still arguing about.
Yeah, I can wonder. I wonder as well. So this is very interesting. Do you have any idea how much volatiles this rhyolite magma had? I mean.
Yeah. So we get quite accurate measurements from the FTIR on the volatile content. Whether I'm going to be able to get the number right offhand, it's not much. It's on the order of, is it 1%? I think it's around 1%.
Right.
And so, you know, as petrologists, we use the amount of water and the amount of CO2 to estimate the depth, right?
Yes.
So, and this is a common way we work out how deep our magma chambers. And the interesting thing is, this amount of water doesn't, if you just say, okay, the weight of the continental crust in Iceland is this, it doesn't correspond to how much water is in there at depth. So we know it was 2,000 meters down, basically, where we hit it. And 1% water doesn't equate to 2,000 meters.
So the overburden there,
of rock.
yeah. Wow.
But if you think about the overburden, if you think actually, well, maybe the overburden is not just the overburden of the rock, maybe the hydrothermal system is actually making it less heavy, if you can imagine, right? If half of that material is filled with water, then the overburden is a bit less. So if you play some games there and think about, oh, okay, some of it.
So if you're basically assuming that the density of the overburden is less than solid rock, that's what you mean. Yeah. Then I get you. Yeah.
Then you can make it match.
Yeah, of course. If it's porous basalt and you're adding water, then you know there's some room to play with, because if you add a porous basalt and you measure it and you add water, it might even be higher than your initial estimate. But I can see there's variations possible. Very good. You have some little thingy on your computer as well.
Yes, so another big part of this project is this kind of big picture. You know, this is something that kids, I mean, I'm a big kid myself, but this is something that kids can get excited about. And you know, it's like going to the moon, right?
Absolutely.
So we've made a whole series of this is Magma Drillers Save Planet Earth. So we've made...
Oh, fantastic!
We've made a whole series of funny videos for kids where they get to play a game where they actually have to work in teams and they have to choose where to drill. And so they have to use the information that we give in the videos, and they have to try, okay, I'm going to drill here, this deep, I'm going to use this type of casing, and then they get an outcome, you know. well done, you've blown up the world, you drilled too deep, or you know, or you haven't drilled deep enough, nothing's happened.
This is very good. I remember as an undergrad student, we had to do these calculations about where to put drills for finding oil. And of course, I mean, if you drill too often, you're wasting a lot of money. If you have too few drill holes, you might be missing your target. And this is a good exercise, and getting people to think about it at an early age, about the complications there, is very good. Also, I think kids will be fascinated by these ideas, by the idea of finding magma or drilling into it.
Yeah.
But of course, there's always this accidental or random component, because at Krafla they didn't want to find magma, right? So, and whoa, that's there will be a lot of adventures in the future, I think.
There will be a lot of
So, this Krafla Drilling Project, how can people ensure that they're going to find magma this time? I mean,
basically, we're going to drill in the same place.
Right.
So we're going to drill right next to it. I mean, there was talk of actually going straight back down the same hole.
Okay.
But I think actually we're going to just go beside it. And so we know there's magma there.
Yes, yeah. Maybe it's there's a little bit of a crust or so, but that should not be a major hindering reason.
Yeah, I guess we'll find out how much the magma chamber is cooled in the last.
That's actually interesting.
10
years,
gives
you some extra information. Great. Just towards the end, I mentioned it earlier. NASA had these. Well, they released a bunch of future ideas about how to save certain things, how to save the Earth, and one of them was supervolcanoes, and that we could, in theory at least, calm supervolcanoes down by putting a lot of drill holes in and letting them cool out and things like that. Whew, my first reaction is, God, if the supervolcano is in unrest, if it's rumbling, then it's not a place where you want to actually go. You certainly don't want to be the driller there, but what's your feeling on this? Do you think there's hope for us being able to do something like that in the future? Imagine that Yellowstone is starting to rumble, and you know, we bring our, I don't know how many we need, but probably hundreds of drill rigs and try to sap the energy. Do you think that's reasonable?
I mean, I think on the time frame of maybe our lives, this is possibly unrealistic and reckless, right?
Yes, I think so.
And the beginning of a bad science fiction movie.
Yes.
But I think, you know, with the Krafla experience, and if we can be successful in this endeavor, it's the first step that maybe in 100 years, 200 years, you know, maybe we can actually harness the energy of volcanoes.
Yeah.
And, you know, maybe you can generate a lot of cheap and sustainable and environmentally friendly power from magma, and then at the same time you cool down those magma chambers. And theoretically, I mean, people have done the calculations, you could cool down magma bodies on timescales, and like you say, you've got 100 drill rigs all pumping water down and sucking this numbers of joules per year over the spaces of hundreds of years. Maybe you could, and you've got your finger on the pulse, so if something unrest does happen, you're going to know first because you've got a drill hole down there. Yes,
it's reminding me of a conversation I had with Paul Younger. He was an engineer from the University of Glasgow. He passed away a few years ago, but he was big into geothermal applications. And of course, he always stressed that there's a risk of, say, magma replenishments, and it could mess up your whole system. But if you are making profit within 20, 30, 40 years, and you dismount the whole thing after a while without any major loss of equipment, then this is actually financially attractive, and we could indeed potentially harvest energy. I mean, many volcanoes have major eruptive cycles of tens to hundreds of years, and in these windows, this is what we need to exploit. Of course, we cannot prevent volcanoes from erupting, but if we manage to get these windows to work for us, then this is reasonable, I think. So yes, as an emergency tool to prevent a volcano erupting, I don't think we're really there, but in order to harness energy and harvest the energy, that I think is a very useful thing, and I agree with you on that one. Wow, great times ahead, so future is calling, isn't it?
Future is calling.
Okay, Ben, thank you very much for all the information, thanks for the chat, and I really appreciate that, and well, fascinating idea. So, thank you for joining us, and well, we'll see each other soon, I guess, and I'll say bye-bye now, and see you later.